Okay, can people remote see my entire screen of the actual slides for today?
Yes.
Okay, all right. So let's get started. So today we're going to take a small break from your favorite Jupyter notebook. Today we're just going to talk about how visualization combine with ethics. I know Professor Anna Little has gave a general introduction to ethics in data science. Today we're going to look specifically using visualization as a tool to explore and understand and mitigate biases in word embeddings, okay? And to start, this is actually based on my research work with a bunch of collaborators. Achit is a PhD student at Utah. Sunipa is a postdoc at UCLA. Jeff is a professor also at School of Computing, same thing with Vivek, NLP expert at School of Computing. And then the rest of my collaborators, Yan, Michael, Jupen, and Wei are actually from Visa Research. And when I say Visa Research, this is a credit card you have in your wallet. All right, so here's a subset of my co-authors where this work first started as a triple AI and KDD tutorial, and most recently is one of those machine learning conference in Europe's demo. So I just type in the GitHub page over for people who are remote, and for people who are here, you can access this link through the Canvas announcement. It would be nice if you can install it on your computer. If you fail to install it, you can also run with that link right there, which is provided by my PhD student Achit. It's just, he just started a server, and I think we can support between 30 to 50 students, but if it's running too slow, let me know. Okay, so what I have indicated in red is that this particular lecture would contain examples of stereotypes seen in society, especially in language representations, that may be potentially triggering. So I just want to put this up here. The biases you in C are inherited in the natural language data sets that you use. It does not represent any of the opinion from the authors themselves. Okay, so you ready? Let's get going. So there's actually a really nice YouTube video that is Kate Crawford's Europe's 27 keynote, which is talk about the trouble with bias. And I kind of put this timeline here. If you, like I said, in your spare time when you are procrastinating over YouTube, this is actually a really nice YouTube video to watch. And she went into details of motivation of why we want to worry about biases in word embeddings. And today I'm just going to give a very brief overview of those biases and how to mitigate them from an algorithm perspective. And the tool we're going to use is developed using D3.js. Remember last lecture, we talked about how you can do with Altair and all those packages to enable interactive visualization. If you want to build more custom ones and more advanced data visualization, JavaScript, which is D3.js, is currently the state-of-art tool for doing that. And you'll see an example when you start playing with the demo. Okay, so what are world representations? Oh, by the way, I also want to advertise sometime down the semester, I believe is after spring break, we are going to have another guest lecture, which is focused on natural language processing. So today you're only going to see a small aspect of this, but a lot of language processing nowadays rely on what I'm going to say next, which is this word representations. Almost a lot of more advanced. So if you talk to your Alexa, right, say, Alexa, where's my package? There's, of course, voice recognition, and then there's also natural language processing underneath that. So again, this is not a lecture on natural language processing by itself, but as part of the data science, it would be good for you to get an essential understanding. And I believe the interfacing between visualization and natural language processing is actually a very interesting one. So how many of you have a good sense of what is word embedding or word representations? Raise hand? No? Okay, good. So this will be new for many of you. Good. So representing meaning of words. So if you actually see, as human, you see a picture. I have a very black cat up there. That's a cat picture. If you see a cat, a dog, a tiger, and a table, if you perceive them as images, your brain is going to process them to say, okay, through my visual cortex, I recognize those are animals versus objects. But now, if I tell you the word cat, dog, tiger, and table, in some sense, you are already processing those words and associate meaning to it. But now the question is, what do those words mean for a computer? And how do we obtain their meaning for a computational purpose? So especially for language technologies, is how can we represent the meaning of those words in the form that is computationally flexible? And then the underlying hypothesis is what's called distributional hypothesis, is that if I were going to find a representation for my words, then words that occur in the same context should have somewhat a similar meaning. So for example, just looking at the words cat, dog, tiger versus table, if you are going to create some representation for those words, the cat should be closer to dog, should be closer to tiger, and should be relatively far away from table, because there's roughly two categories of things where whatever your representation you came up with has to be closer for cat versus tiger, but further away in terms of table. Okay, so that is sort of the first hypothesis. Now let's look at sort of what we call symbolic versus distributed representations. So what I mean by symbolic, right? If I say the word cat, tiger, dog, table, they are all symbols, right? In fact, of course, throughout this lecture, I'm going to just talk about English language. The same kind of biases we're going to discuss exist in other languages as well. So it's not universal to just English language. So if they're just symbols, if you just know the symbols themselves, it actually doesn't tell us what they really mean. So what I mean by that is that conceptually, cat and tiger should be closer to each other than, say, dog versus table, okay? And then cat, tiger, and dog should be closer to each other than table, okay? So this is sort of like an intuitive thing, but if I just treat them as strings, right? And thinking about the proximity between string, for example, the string apple is closer to the string eagle, oh, not eagle, let's see, atlas, for example, versus it's further away from the string, say, yellow, but the proximity in terms of the string themselves does not capture anything semantically, right? So we want something more advanced. We can't just compare the string with each other. So this leads to the first thing, what we call one-hot vector encoding, okay? So of course, it does have its drawback. For example, in this particular case, if I do one-hot vector, it still does not capture inherent similarities, but let's see what one-hot vector does, okay? So let's say I have a vocabulary, and then that vocabulary contains 4 words: cat, dog, tiger, and table. And I want to encode those 4 words in this one-hot vector. What I do is essentially there's a 1 if that particular, say, sentence contains the word cat in the first position. And if it contains the word dog, it has 2nd position, contains the tiger, the 3rd position, and table is the 4th position. In other words, from Wikipedia, the one-hot vector is a 1 by n vector used to distinguish each word in a vocabulary from every other word in the vocabulary. It consists 0 for all the cells, with exception of a single one in a cell used uniquely to identify the word. So if my vocabulary or my dictionary is very small, it only contains 4 words, then the one-hot vector encoding for cat, dog, tiger, and table is precisely looking like this, because this is saying that I have 1 cat show up and then nothing else. For the dog, it has the word dog show up and nothing else. The problem with this one-hot vector is, okay, I did came up with a representation of each of my word, but the problem is that the distances or the dot product are all equal. So in a way that if I'm treating it as a vector and I'm start computing Euclidean distances between those vectors, the distance between cat and dog is the same distance between cat and table. Because if you think about Euclidean distances, they are all equally spaced out from each other. So this is not ideal. Let me bring this. So then what do we mean by distributed representation is that it's trying to capture conceptual similarities slightly better. So instead of being a one-hot representation, like 1-0 representation, it's actually become still a vector representation, but it's kind of try to adjust for its similarities and differences among the semantics of the words. How do we come up with those? There are some various ways. For example, modern technology is based on neural network. So you kind of train a neural network to come up with those embeddings. But if you see visually, the difference between this and then the previous picture is that it's no longer this 1-0 encoding. It's actually a vector encoding that has non-zero entries across some of those dimensions. So in this particular case, of course, you can imagine the cat will likely have, say, an entry of, say, 0.9 for the first entry and 0.8 for the second entry. So now each of those things is now a real valued vector, not just 1-0, but real valued vector. And then the way, let's delay how you came up with this first. But if you have this kind of what we call distributed representation, the idea is this new vector representation now is a real valued vector will capture the fact that if I compute the distance, or in this particular case, you can compute things like cosine similarities, the cat and dog and tiger, or say, let's say cat and dog are closer to each other in terms of their distance or cosine angle than from cat and table, okay? So that's the difference between one-hot encoding and distributed representation. Let me give another example in this case. If I have a sentence now, right, instead of single word, I have a sentence. And the first sentence is, have a good day. And the second sentence is, have a great day, okay? Again, I'm going to build a vocabulary out of this, again, using one-hot example. The one-hot example is building on the dictionary that is just a union of all the words you just saying. So there's 5 words. Now, again, I'm going to say it's a 1. If that word show up, it's 0, it's not show up. So now what you have is that the word have is 10000, the A is 0100, and so on and so forth with respect to this particular dictionary or particular vocabulary. Now, the interesting thing is, again, using those one-hot encoding, if you look at the word good and the word great, if semantically those 2 words should be fairly close to each other, right? Because they have similar semantic meaning. But the problem is, again, in this one-hot encoding, the word good and great has a distance the same as the word day versus have. Because again, the Euclidean distances is exactly the same. So now if I replace one-hot representation to this distributed representation, the idea is, again, going back to this picture, is that every single word is going to have this real valued vector representation such that, if I take the cosine similarities between their vector representation, the 2 words, if they have semantically similar meaning, should have a small angle, which means they're very similar, versus words that are different semantically are going to have a big angle. Yes?
Would the magnitude always be the same?
No, the magnitude you will see in the projection, actually. We're going to play with a lot of word projections today. Okay. Now, this is sort of one of those concepts behind the things called word-to-vect. The idea is we want to introduce some dependency of one word on the other in terms of the vector encodings. Again, this is another example. There's many examples. If I started the word king, the king is translated hypothetically to a 4-dimensional vector, right? It has a vector of 4 values and it's color-coded. And then the word man is going to color-coded too. The word women is going to be color-coded. And then the idea is that perhaps king and man, well, of course, later on we'll talk about, right now for simplicity, we're going to talk about genders as if it's binary, but we know that gender is not actually binary in modern society, so we're going to delay that discussion later. But in some sense that you can imagine the word king and man maybe closer to each other than the words between men and women in terms of the corresponding semantics. Okay. So I have talked about this word embeddings. What we want to achieve, which is what we call distribution hypothesis, is that if two words are semantically similar, they should have a very similar vector encoding. So how do we achieve this mapping? There are what's called context-independent vectors coming out of what's called Word2Vec, GloVe, and FastText. Those are all previous work. And then specifically for our visualization today, we're going to use the GloVe embedding. And you're going to see an example of that. And there's also things like parameterized mapping produce context-dependent vectors. The most sort of widely used one, a variation of BERT. And BERT is essentially what's boiled down to, in a lot of cases, it's a trained neural network that it takes a bunch of input, it obtains the sort of embedded words and sometimes produce the actual embeddings through a neural network. So when we talk about embedding, sometimes I'm going to use the word vector interchangeably. When I say a word vector, it's basically a row of real value numbers where each point captures a dimension of words meaning and where semantically similar words have similar vectors. Okay, so in a lot of modern day neural network, natural language processing tasks, that word embedding plays a very essential role in it. Okay, but we're not going to go into detail how you obtain that. We're just going to use some existing ones, and GloVe is one of those more popular ones. So just revisit the word embeddings. The idea of each of those word embeddings is they capture distributional semantics. So when I say low dimensional vector, when I say low dimension, I really mean 50 dimension or 300 dimension in compared to really high dimensions, okay? So in a way that the ones we're playing with today is 50 dimension, but what you're going to see is the actual 50 dimension projected into 2D for visualization purposes. But the idea is how do you, the embeddings are what's called distributed semantics is because the idea of those embeddings is again, the principle, if they're semantically similar, they should be close to each other in terms of their angle or in terms of their distance. The dimension of the embedding represent different aspects of the meaning, and words are characterized by membership to those latent dimensions. When I say latent dimension, it means, let's say today we're looking at 50 dimensions, so each of those dimensions is called a latent dimension. They provide features, they are widely used, convenient learned feature representations. So a lot of modern day natural language processing tasks rely on the usage of those word embeddings. Of course, you know, I'm sure there's like multiple lectures you can talk about in word embeddings. The idea is the common theme is you're going to use massive unlabeled text corpora, for example, Wikipedia or news articles. And then you basically set up what's called a surrogate learning task that does not require the label data and produce embeddings as a side effect. For example, things like BERT, which is a neural network, will produce those word embeddings along the way. So for example, if you have the particular text, it says it was dark at night and so on, you're going to define a neural network of the form of, you know, finding embedding that probably for the hidden word being stormy. So in a way that this is a particular task that is going to complete that sentence, right? It was a dark and stormy night and so on and so forth. So it's actually trying to predict what words is going to fill in that sentence. But in that prediction process, it will actually also produce the corresponding word embeddings as a side effect. And last bit I want to talk about is that you can actually evaluate word embeddings. So you can kind of look at what's called intrinsic and extrinsic evaluations. I'm just going to talk about, for example, in extrinsic evaluation is that you want to look at the impact of the representation on another task. And in that particular case, when you evaluate over some of those tasks, it might be slow, and depending on the quality of the model for the task being tested, that extrinsic evaluation. Intrinsic evaluation is using very simple task, looking at whether it's success or failure. It's easier to compute, but doesn't say much about the embedding as features. So we're not actually going to talk about evaluation of this, but we're going to see the biases that exist in those word embeddings today. So this is where ethics come in. So this is a famous quote. Feeding AI system on words beauty, ugliness, and cruelty, but expecting it to reflect only the beauty is a fantasy. So what does this mean? Is that if I have some natural language processing task, it's trained over those word embeddings that is coming from natural language, say Wikipedia news articles, whatever beauty or ugliness that exists in the society would be carried over, somehow expecting the word embeddings to not be biased is an idealistic stream. Okay, so we're going to see a bunch of those examples today. Essentially, if word embedding capture distributed information from text corpora, and those text corpora process society stereotypes, then the trained word embedding will include those stereotypes. So biases in language technology is a very fast-moving field with new technology and perspective introduced almost every month. There's two relative lines of work. One is new methods for quantifying biases, including embeddings, and then two is method for removing those biases from the embeddings. So we're going to mention a little bit over topic number 1, but we're going to focus mostly on topic number 2. First of all, let's observe the biases in the word embeddings. And then now let's think about algorithm ways to remove those biases. So what is a bias? This is, of course, a more mathematical definitions. Is that, well, I'm going to look at the difference between estimator and expected value. So, so for example, the red circle or the red star is where the expected value is. The actually estimated value is the green square. And then their distance is sort of talking about how much does my estimated value deviate from my expected value. That is one definition of bias. The next one can be an instance of prejudice, especially a person and sometimes unreasonable outlook. For example, in machine learning, a stereotype, and so on and so forth. There's also a bias definition, which is an oversimplified view or prejudice attitude of a particular type of person or thing, or an oversimplification of a concept. So what do I mean by that? Here is some examples of oversimplification of a concept. Children are always curious. That is oversimplification, right? Dogs are always friendly. If you ever get beaten by a dog, that is not a true statement. Nurses are women and doctors are men. This is a very, very typical gender bias, which associate certain occupation with certain gender identification. And usually some of those oversimplification comes with a negative connotation. So in this keynote, there is specific type of harms that might have been caused by biases. The one is what's called allocation harm, is that if you, let's say you're training a machine learning model to try to automatically decide on entrance or college admission, or if you have machine learning model that is deciding on who is getting a loan and who is not, or if you have a model that is giving you advice whether you're going to give someone a parole or not, those are allocational harms that might have caused through machine learning models. There's also what's called representational harm, and that's actually what we're going to look at quite a bit today. They are sometimes more subtle, how data is represented, which leads to negative stereotypes. So here is a very, this is a pretty, use quite a bit of a screen capture. If I type in African-American names into Google search, sometimes the sort of ads by Google will come out to say, well, this is associated with somebody's arrest record. All right, and then this is one particular example of a representational harm that is associated with a certain subgroup of people. So in this particular context today, we're going to use a specific bias definition is referred to stereotypical association between words or group of words that may cause representational harm. For example, a subordination of a certain social group along the lines of identity, right? And also I want to emphasize when we talk about biases, it's multifaceted. It's not just one type of bias. It's actually, there's, even later on, we can talk about biases against royalties. And knowledge representation is a big part of AI. So now if I'm telling you there are biases in the word embeddings and you are using those word embeddings to train AI models, that is going to influence the prediction and decision made by those models. And of course, they manifest through the training data, how those data are represented, and how the machine model is used. So source of bias. If I train my word embedding based on, say, Wikipedia article, and in Wikipedia article, there's a lot of articles associated jobs with gender. For example, nurses are typically female, engineers are typically male. If those gender biases exist in your training data, and when you train those to get your representation, those is going to inherit it through your final representations. There's also algorithm bias, which is biases that's retained and amplified by the algorithm themselves. And also there's bias in data for training of specific tasks. So in order to measure sort of biases, there's many measurements. I'm just going to emphasize one because this is one that is encoded in the software we're going to play with. Let's say I have a bunch of definitionally male words, for example, man, male, and definitionally female words like women or female. But then I have a set of stereotypical male professions, such as programmer, engineer, scientist, or a set of stereotypical female professions, which is nurse, teacher, librarian, and so on and so forth. The idea is that we're going to compute what's called a weight score, which is implicit association test. And then the idea is, if you look at the second equation, the first equation here is looking at association of gendered words with each of the set A and B. Okay, so this is a mathematical computation. And the second equation is what the weight score is trying to do. It's looking at how much sort of stereotypical male professions affiliated with definitional male words, and same thing for the female professions versus female words. And the idea is that if my embedding is actually gender neutral, then this score should be 0, okay? However, most of our word embeddings are not. So if you actually use the famous word-to-vec embedding, its score is 1.89 versus GloF is 1.81. So it's far from being gender neutral, okay? So now let's look at some of the methods we're going to use to remove biases from word embeddings. Before I do that, I need to first tell you how do we define sort of bias direction, okay? So one of the things that you can remove bias is through different ways. One is you can modify the process that is used to generate those representations, but it's typically more expensive. So what we are going to resolve to is what we do post-processing. So there is this model, say a neural network, that generate a bunch of embeddings, and we're going to observe and detect the biases in those embeddings and apply algorithm to try to remove it, okay? And this is what we're talk about is debiasing through post-processing. It's inexpensive, and you can see today that in the demo, everything is computed on the fly. So it's pretty efficient. So before we do debiasing, the first thing we need to talk about what's called feature subspace determination, which is basically find the direction where the bias is. And throughout today, I'm only going to talk about one type of bias at a time, okay? So I'm going to use the gender bias as specific example. And for simplicity, I'm going to treat gender as a binary for now. So let's say the first method is called PCA pair. Okay. So PCA is principal component analysis. If you give me a high dimensional word embedding, for example, in 50-dimensional word embeddings, I can find the dominant direction of that point cloud. Okay. So when I want to define, for example, in this case, a gender direction, what I'm going to do is I'm going to collect a number of pairs of words that is sort of the opposite gender along the stereotypical gender direction. For example, boy versus girl, he versus she. And now the idea is we're going to find the differences between those vectors. We have 2 points. The arrow between one to another is the difference between those vectors. And then among all those directions, I'm going to find the first principal component to define the gender direction. So roughly speaking, if you look at, I have 3 pairs words, man versus woman, he versus she, boy versus girl. There's a direction going from boy to girl, he to she, man to woman. Among all those directions, I'm going to try to find the rough direction, which is my red arrow, and that is my gender direction. Yeah.
Sorry, maybe you already said this, but like, what is the axis here? Like, why is boy on the negative?
Oh, those axes. So I didn't tell you is that the underlying point cloud. Remember now, every single word is represented by a 50-dimensional or 300-dimensional high dimensional vector, right? And what I'm visualizing is I'm just projecting them over some dimensionality reduction techniques, and I project it. So what you're seeing, the x and y axis don't have a specific meaning. It's just correspond to the 2 dimension I choose to project them. Does that make sense? What really matters is actually the direction. So in this particular case. So what I'm trying to define is among my word embeddings, where is my rough gender direction, okay? And then in the PCA pair way of defining the direction is looking at for pair of gender opposite words to find the average direction along there. Yes.
And so does it matter that it's moving from boy to girl as opposed to girl to boy?
It doesn't matter. Yeah, it doesn't really matter, but ideally you want to kind of go into one direction, because if you're doing other direction, depending on whether you take the absolute value or not, you might cancel things out. But yeah, but the direction is you know, in some sense, the line, the general direction, whether it's this direction or the opposite direction, define where the gender differences are. Now, the second type of direction, sort of define bias direction, or define the subspace, if you take a bunch of words together. So in this case, again, boy, girl, he, she, women, man together, and we're going to find the first dominant direction. And then this is basically try to capture the direction where a lot of biases might be associated with. And again, in this case, I have those 6 words. I'm going to try to find the most dominant direction, again, using principal component analysis. And I'm going to define the first primary direction of those vectors to be the gender direction. The next one is what's called 2 means. If you have 2 group of words, again, I have a set of names that is statistically / stereotypically female names versus stereotypically male names. What we're going to do is for all the female names versus all the male names, for the female names, I'm going to find a center or a mean. And for the male words, I'm going to find a center or a mean. And the direction between those 2 means is the gender direction. All right. So for example, in this case, the 2 black dots, one on the left is the mean of the stereotypical male name. And on the right hand, the black dots among Victoria, Carolina, Mary, that is stereotypical female names center. And then this direction also defined what the gender direction is. And the last bit is another method is called classification boundary. So if I want to find a classifier that separate stereotypical male words and stereotypical female words, that is a black line right there. And then the direction that is orthogonal to that direction or normal to that direction is now the gender direction. So if you think about, here's a bunch of stereotypical male name, stereotypical female name, here is a boundary. then the direction is orthogonal to their classification boundary. Okay, so those are different ways to define direction. Now, what I'm going through fairly quickly is the different ways to define the bias direction and remove the bias direction. And we're going to do this through animations, through interactive visualization. So first of all, this is called linear projection. And oh, actually, I'm going to give you a 5 minutes break. And then this is the time where we're going to start playing with that software. So after at 4:22, I'll come back and we'll start doing a live demo in combination with the debiasing technique. So you can have a very sort of concrete understanding of what I mean by bias and how do I mitigate those bias. So 5 minutes break. And for people who are remote or people who are here, you can try to install, let me actually go back to the software itself. You can try to install the software on your own. Yeah, so this is a third link right there. If not, you can also start playing with the fourth link. Okay. Yes.
Does this mean that it's working?
Yes, and then you can just open our browser.
Okay,
And then
copy that.
Yeah, copy that. It should be working. Yeah.
Okay.
Can people see for people who are remote, can you see my shared screen
Yes.
Yeah,
for the
has a
software?
gender. Yeah, it has a gender and the nurse engineering.
Perfect.
Yeah.
Yep. For people who are installing, this is sort of the software where you're going to, if you want to do a bit more The one that come, or let me resume my lecture. I just started. So if you actually look at the software, can people see the verb GitHub page remote?
Yeah, we can do that.
Yeah, so TA Hao Yu, can you help the student to figure out how to install? If not, you can open, for people who can't install it, open the link that is the 5001 link. That is a live demo and you don't have to install anything if you're having trouble install it. But I want to emphasize for those of you who just installed it, the default one is, like I said, is a 50-dimensional embedding and it's trained over Wikipedia 2014 GigaWords 5 corpus. If you want to use a bigger one, there is another one you can download that is slightly bigger, and then you can play with that embedding as well. So this software is designed, you can provide your own embeddings. But right now we're going to go with the GloF 50-dimensional embedding. So let's get a sense of what I mean by debiasing. Okay, so remember the point cloud that I'm playing with is 50 dimension, but I'm just projected into 2 dimensions. So you can actually see the relative, of course, when you talk about dimensionality reduction, there's going to be some distortion, but the idea is in the projected screen space on the right, you're going to still see some relative positions or proximities between those words in the projected space. And also another thing is that I only showed a small, tiny subset of the words, but when I'm debiasing, I'm actually applying the algorithm to the entire large embedding, okay? So the first example, which is the most simple one, and if you understand this one, I feel like I achieved my goal for today's lecture. This is the most simple way of debiasing the words. So what do I do? This is called linear projection debiasing technique. And if you click on the example right now, click on example number 1, which is looking at gender bias associated with occupation. And in this particular example, what you see here is I'm going to use subspace method. Remember, I just went through 4 different, actually, there's a 5th one, which I did not go into detail. But for this time being, I'm going to use 2 means to define my gender direction. And then in order to do 2 means, I need to provide 2 groups of words. He, him, she, and her. Those are 2 separate group of words. I'm going to compute the average vector for each group, and their direction is their gender direction. Okay, and then I'm going to evaluate, given the current word embedding, what is the gender bias associated with the current embedding? Remember, this is one of the most commonly used word embedding for tasks. Yes?
Sorry, can you define embedding?
Embeddings are representations. Those are high-dimensional vector representation of each word, right? So think about the word him. This is represented currently underneath the hood. The word him is a 50-dimensional vector, okay? And this is already provided to you, okay? Now, each of those words is a 50-dimensional word. I'm just projected onto 2D, so that's what you see on the right. And the first thing I'm going to do, the black arrow with the arrow gender is actually where the gender direction is defined right now, based on the 2 group of words, him, he, him, and she and her. But the first thing I'm going to do is I'm just going to rotate the direction. I'm not doing any manipulation of my word embedding. I'm just rotating the direction. So this way, my bias directions always along the x-axis. In this case, the gender bias is along the x-axis. So keep in mind, I have not done anything to my word embedding. I just changed my viewing angle. Okay, I just rotated my embeddings. Okay. Now, can someone tell me, can you observe the gender bias already in this embedding? All right. So what do you see? You see that the gender direction is defined by this 2 group of words, and it's along the x-axis direction. And you see the occupation. There's 4 occupations: receptionist, nurse, banker, engineer. The problem for this bias, gender bias, is that there is a stereotypical association between certain gender and certain occupation. In this particular case, you can see, can people remote see my mouse? I hope you do.
Yeah, we can.
Okay,
Yeah.
You can see that receptionist and nurse is much closer to the female words versus banker and engineer, okay? In fact, this is designed where you can input your own words. What are some of the gender typical words you want to play with?
Homemaker.
Anybody else?
Manager.
Manager, yeah, that's an interesting one. Okay, so now I'm just changing the evaluation set, so I'm going to rerun everything. Hopefully manager is in there. Okay, good. I just updated my words. Again, I'm going to do a reorientation. So I'm not changing anything, okay? Okay, you should see that the word manager is still typically extremely female or male versus home worker is still typically also very on the female direction, okay? Now, let's talk about this exists in there. What is an obvious way for me to actually try to remove this bias from my word embedding? This is the first algorithm called linear projection coming. The idea is if I take those occupation and I project it along the x-axis, they have very different coefficient. In fact, you can think about the receptionist, homemaker, nurse, all those words has a coefficient that is closer to the female gendered words versus banker, engineer, all those has a projection more towards the male direction. One way to try to remove biases is to make sure if I modify my point cloud such that when I project it along the gender axis, there's no longer a preference towards one gender versus other. In other words, I'm going to change my underlying embedding. I'm going to change all of them, but I'm only going to visualize the ones you're going to see on the screen right now. I'm going to modify the embedding such that their projection along the gender direction is not differentiable. That's precisely what we do. We're going to modify through algorithm ways the underlying point cloud, which is this word embedding, such that now I have changed those words that their projection along the gender direction have the same coefficient. So there's no longer a gender differentiating coefficient. Is this still making sense? Okay, so the idea is to remove the differentiating factor of those occupation along the gender direction. Now, the next step I'm going to do, I'm not modifying the words, I'm just changing my viewing angle. So I'm just rotating my viewing angle of this embedding. And this is what you see now. You see that now in this embedding, the homemaker is actually closer to the word he, and receptionist is more close to the word him. So in a way, I am completely removing, well, actually to some degree, I'm removing the association of occupation and gender. So far, so good. If I can go back all the way to the beginning, you can also see that without me changing the viewing angle. In the beginning, when I have she and her, you see all the occupation that is more stereotypically female is associated here versus the stereotypical male words is more closer to the word he. But after my debiasing, this is again just changing the angle. And then there's a small explanation right here, what each step does. And then this is, we remove the component along the concept direction. In this case, the concept is gender, and I reoriented. So after this operation to my underlying embedding or word representation, I have removed the gender bias to some degree. Yes?
In that one step, I guess where they all came up on the vertical axis, why did the gender arrow not change, I guess?
Oh, yes, I'm not recomputing the gender direction. This is my original gender direction. Okay, so this is sort of my defined gender direction, and I'm going to change all the underlying word representation or word embedding such that their projection along the gender direction is removed. Okay, let me give you another example. Again, let's stay with linear projection because this is the easiest one. There's a royalty. Okay, so what are the words we provide here? Again, this is linear projection to means. The set of words, I'm going to define a direction. This is what I call royalty bias. Not sure how much societal impact this is, but if you think about two groups of words, king, queen, prince, princess, one group of words. The other group of words, man, women, boy, girl, okay? So more commoner words. And then again, the direction is that I'm going to compute the average location among all those words on the left set and all those words on the right set. And then their direction is what I call royalty direction. And I'm going to evaluate those adjectives that is used to describe people and to see how those adjectives are associated with the different groups. So again, the first step I'm going to do is I'm going to orient my data sets a little bit. So my royalty direction is along the x-axis. So what you see here is, for example, along the more royalty words, the majestic is closer to the royalty words versus the word, for example, obnoxious is more close to the commoner words, okay? Again, you can modify those words on your own and then look at what exists. So again, I'm going to apply the same thing. If I want to remove this particular type of bias, I'm going to shift all words such that their projection along the axis is 0. So the coefficient doesn't have a differentiating factor. And I can reproject it or change my viewing angle. Okay. So all right, let's go back to the slides itself. So this is the most simple example, and then there's a few slightly more involved thing which we're going to go through one by one, and then we're going to play with the software a bit more. So what we have seen is what's called linear projection. You have predetermined bias direction. In this particular example, we use gender. We try to remove for all the words this, let's use gender again. We want to remove all the gender bias for all the words. So when you see the animation, why shifted, all the words is shifted so that their projection along the gender axis is the same, okay? The next one, so if you now look at my small animation on top, this is, the red is my bias direction, and all the words is I'm going to change all the words with their underlying representation or embedding such that their projection along this direction is all the same. And then I'm just going to change my viewing angle. That is linear projection, which is what we have seen. The next one is called hard debiasing. And this one is slightly more involved. Is the idea is you have those dark green nodes, and those dark green nodes are the ones I'm going to use to define the bias direction. But I do not want to change their relative position. I do not want to modify their actual embeddings, versus linear projection is morphing everybody. This particular hard debiasing is trying to retain some of those. For example, if you think about gender biases, right? In a lot of cases, you might not want to remove all the gender information from your text. Maybe some of the gender information is still important for your training task. So the idea is I want to debias, but I want to maintain some of those information still. So now, again, let's go back to the example here. If you click on example, there's what's called hard debiasing gender occupation. So this become slightly more interesting, but it will become more obvious when I start animation. So in this particular case, I still have the two set of words that define my concept. So let's say my concept is still gender. I'm just changing the label of the concept. It's still gender. And in the first step, I don't do anything except I'm just changing my viewing angle. So if I have a camera looking at my projection, I'm just changing the angle a little bit. So this is still the same type of gender bias, occupation associated with gender direction as we've seen before. Now, what I want you to pay attention to is in the debiasing technique themselves. If you actually see what has been modified in this particular case, let's go back one step. is all the words that is in blue, which is the occupations, all the words that is in boy, girl, him, and house, those are the ones that got modified. But the ones that I keep intact and didn't modify, it's called are what's called are the gender directional words. So the words he, she, he, and him, those are the ones that is used to define the gender direction, but I want to somehow retain them and not modify them. So that's what's the difference between this and the previous. And again, after I did this operation, I am going to, so the difference, now this is interesting. So the difference is that, first of all, okay, let's go back to the very beginning. I have the projection as before. I change my viewing angle. I touched all the words so that the projection along the axis is the same, except for the gender defining words, the gender direction defining words, he, him, she, and her. So those words has not been moved. But also one additional step is those what's called equalizer set, which is a word boy, girl, he, and her, and him. I want to kind of go back and return their information. So I still want to return some amount of gender information, but I want to remove the bias association between occupation and gender. So in this particular case, what I'm going to do is I'm going to actually bring back the embeddings for, or recover the embedding for girl, her, the word girl, herself, boy, and himself. But I have removed the association of occupation with gender. And then the last step is to just change my viewing angle again with this embedding. So the difference between this method and the previous linear projection method is that I still want to retain some information of gender in my embedding. I don't want to completely remove gender direction, okay? But I want to remove the association between the occupation and gender. Okay. All right, let's look at the third one. So again, a recap is the green pink words that what we see are used to reintroduce meaningful gender information in a controlled way. So I don't want to completely lose my gender information in my embedding, but I want to reintroduce it. Okay, so that's hard debiasing. And again, if you look at this, my short animation on top, I have this, I keep the green point intact, but I'm going to reintroduce the gender direction using the orange and pink. Oh, sorry, the light green and pink. Now the next one is called iterative null space. It actually calls linear projection as a subroutine. Okay, so let's look at the demo. So if you choose here, iterative, INLP. Okay. So again, I'm using a lot of gender, but this is a tool where you can create your own words and play with the own biases that you want to detect. So in this particular case, it's still using linear projection as a subroutine, except it's keep removing biases as we go along. So it goes through multiple steps. In this particular case, the subspace method is classification. So what I'm going to show you is, first of all, I have all this bunch of words. Again, you know, some gender words, some occupation. First of all, I am going to find what you see, this dotted line is a classification boundary of the two sets. And then the black line is a gender direction that is orthogonal to the classification boundary. So this is a gender direction I'm going to focus on. And then this step, I'm not doing any modification. I'm just changing my viewing angle again, right? So just, if you have a viewing angle, you're looking at the point cloud from this way, I'm just redirecting it, changing the orientation such that the gender is again along x-axis. Okay. Now, what you do here is you say, I'm going to apply one step of linear projection as before. Okay. And then I am going to, you know, I'm going to remove all the biases along this gender direction by making sure their projection have the same coefficient. And now I'm going to change my viewing angle. Okay, so this is one step of my debiasing. But the argument for iterative method is that maybe after this first step, there might be what's called residual biases. So maybe I have not completely removed the gender bias yet. So what I'm going to do in the next step is to define again the gender direction using a reclassification of my modified point cloud. So in this particular example, there are still appear to be some gender differences in this classification boundary. So I'm going to apply again one more step of linear projection method. So again, this step is just changing my viewing angle again. So my x-axis is my gender. And I'm going to apply linear projection one more step, okay? Again, I'm going to try to remove what's called residual biases. And then this is the last step of returning back to what the end result is. So the idea of this is that at every step of the way, I'm going to remove some biases. And then I'm going to check whether the gender bias is still there. If there is still there with a classification boundary way, I'm going to use classification boundary of the remaining modified embedding to define the gender direction, remove the bias again until there's no more residual biases. Yes.
So, okay, I guess I'm just trying to grasp like why we're doing this in general.
Yeah.
Is it just like we have this thing with 15 dimensions?
So, yeah, so let's go back to the motivation. Let's say I am going to create, and then this has already happened and it has very severe consequences. Let's say I am going to create a specific machine learning model to make decision whether someone coming up for parole, whether I'm going to give that person parole or not, okay? And historically, if I am going to train, like remember, I need to have a machine learning model to train over historic data. And historic data contain biases. So if you train over historic data that has those biases, your prediction is going to inherit that bias. For example, historic data is that, for example, African-American are less likely to get parole than white American, right? So if you don't correct that sort of biases in the training data, then your prediction model is always going to predict, for example, that if this is coming up as African-American, I'm not going to, I have a higher probability of not granting parole versus someone who's Caucasian. Okay, so that's one example. The second example is that, for example, if you're doing resume sorting, if you are based on somebody's resume, and this is where actually a lot of gender biases has happened. This is, how many of you have heard about this experiment they did for interviewing orchestra performer behind a curtain? This is what the curtain thing is invented. So the idea is, if somebody is trying to enter an orchestra, and let's say a violinist, in the actual interview, if it's a female versus a male playing in front of the judge, there are going to be different consequences because that is sort of implicit gender bias in those decisions. And what they have to do is they put a curtain up, and then the judge couldn't see the gender of the person playing the instrument behind. And this is one way of trying to remove some of those biases. What we're doing here is try to remove, for example, gender biases, such that when I remove the gender bias, if this particular word embedding is used to train a model, that gender bias will not be manifested through the model itself and influence its prediction, the prediction result. Does that make sense?
Yeah, I guess I have a question too. Like, how do we know, like, what point are we just deleting data? I have no idea.
Yes, that's a very good question. That's a very good question. For example, Wheat score is one where, so here. So what we have done, if you look at here, is I have reduced the weight, well, I kind of changed the weight score by certain amount, right? So weight score is one way to measure whether how much biases are there. And then you can look at it, you're debiasing until you reduce the weight score to the level that you're comfortable with. That's one way to evaluate, right? There's other evaluations that I didn't go into detail. So there's ways to evaluate, but there's always, remember, everything I'm teaching about so far, the bias itself is what I call multifaceted. There's bias based on gender, there's bias based on religion, there's bias based on nationality, and so on. So it's actually a very complicated question. is that when do I feel comfortable that I have removed enough gender bias without destroying the meaning of my data, right? That's exactly where the hard bias is trying to bring in. The linear projection is removing bias direction for all words, right? So that might have destroyed some information. The hard debiasing is to say, okay, I'm going to do the first step, but then I'm going to recover some of the gender direction because that might still be useful for some of the tasks, right? So you can kind of work on different algorithms to look at what information it's trying to remove and what information it's trying to retain. And then the last one I'm going to talk about is actually, so iterative way is try to remove residual and until I'm in a comfortable level. The last one is orthogonal subspace correction and rectification, which is called OSCAR. This particular method is different than the ones we've seen before, for example, compared to linear projection. This one does not look at removing biases completely. It's actually looking at making sure the two subspace is becoming orthogonal to each other so that you kind of reduce the dependency. And let's say I have a direction that is gender, and I have a direction that is occupation. When those two directions, those two concept directions have a non-90-degree angle, there is some amount of dependency over occupational words and gender words, okay? So the idea of OSCAR is to move the occupation direction so that they become orthogonal. Let me show you the last example here. So OSCAR right here. This is a gender occupation example again for the OSCAR method. In this particular case, what you have, what is going on? It's going to take a while. Okay, so here is what we're doing. The first step, now in this particular case, I have two directions that I care about. One is a gender direction, and one is occupation direction. As you can see, without doing any modifications, those two directions has a very small angle. That means they have some dependencies. That's why you see those gender bias between occupation and gendered words. First step is, again, I'm just changing the viewing angle a little bit. So I have not modified anything. I just changed my camera view of my point cloud. Again, you see this non-90-degree angle. So what I'm going to do is I'm going to try to change the underlying embedding such that those two concepts has a 90-degree angle. So they are less dependent on each other. And that's what I'm going to do. Okay, so, and then now I have the gender direction, occupational direction to be 90-degree, meaning that I try to reduce their dependency as much as possible. But you can still see there's still some gender direction maintained. There's still some occupational direction. So you're not removing the information from the underlying point cloud. Okay. And the last step is just reorienting this. Okay. So in this particular case, you are still seeing some gender direction between, say, the male words and the female words are here. There's still some gender direction. So the gender direction is not completely removed. There's still occupational direction, but the idea is I'm trying to reduce the dependency from one concept onto another. Okay. So what you have seen so far are the main examples of actually 4 of the state-of-the-art debiasing techniques for word embeddings. Okay. So, and then here's sort of like a comparison, but, and we have done these examples, but I want to mention a few quick discussion, and I'm going to use the remaining of the time where we can create examples on our own. So, which bias should we remove? This goes back to your earlier question. There's gender. Do we just want to remove gender? And then the problem is the majority of the gender debiasing right now focus on binary gender. What if gender is non-binary? How do you do that? It's pretty hard. What about other categories? Ethnicity, religion, sexual orientation, those are sort of federal law protected categories. Maybe we should remove those biases. The reason why I'm using gender for these examples is because the signal for the gender is typically very strong than some other measures. But you see this royalty thing. Information is obviously lost in some of those processes itself. So again, this is sort of like a plot of a trade-off over those different methods, like how much gender information is retained and how much stereotypical association is removed, and so on. So, each time you choose a debiasing method, some information might be lost, and you need to think about how to recover those information. And so because bias is documented in many decision-making process, that we do show that downstream analysis, if you actually remove some of those biases mathematically, it shows significant improvement for downstream analysis tasks. So this step is actually necessary for you to have more fair machine learning models. And an important thing is when you are trying to think about biases, what is the context of the NLP application, why it might be harmful, to whom and why. And going back to Professor Anna Little's discussion, there's a lot of communities, even outside of AI, is talking about ethics. So the other aspect is that we might also looking at intersection effect, right? If there's gender bias as well as race bias, how do we deal with that? How do we prove it? How do we remove biases along multiple dimensions? So one of those iterative methods is interesting because remember I showed you example where I iteratively remove gender biases. But what I can do is I can say the first time I do this iterative process, I'm going to remove gender bias. But the next step, I'm going to remove nationality bias and so on, right? So you can do this in an iterative way. Again, this is the point where a lot of those simplified mechanism is treating gender as a binary construct, but how can we extend it to non-binary notion? Okay. For example, some pronouns and words for non-binary or neutral notions are either new or very generic. And some methods don't require this sort of pairings between words. There's also different language models, right? For example, in German, your nouns are gendered by pronoun. In Spanish, many nouns change under gender. So again, what is gender bias in a different language setting, right? And also one last bit, when you translate from one language to another, that translation process itself will also introduce bias, okay? And then there's other type of data. It's not just languages. And this is one component. If you go to our paper, we actually showed biases in merchant data, financial data. It's not just natural language data. As long as there are high dimensional point cloud in representation of some underlying data, there might be certain type of biases, okay? So that's what I want the takeaway. And then this is sort of the paper, if you want to read more theoretical and the design of this visualization tool, this is where it is. But for the remaining 5 minutes, what I want to do, and then this is probably the most fun part, is I want you to play with the system yourself and come up with examples. Okay, so I'm going to give you an example, but I want you to play with it because what you're doing is you're using this interactive interface to explore the different type of biases that exist in the word embedding. And this word embedding is one of the most commonly used word embeddings for natural language processing machine learning training. So for example, this is probably the more triggering thing, but I still want to show it. So this is a nationality bias. Okay, so again, I'm going to reorient my words a little bit. And then there's nationality and associated with adjectives. And then this is can lead to representational harm, right? In this particular case, you have adjectives that is associated with certain nationality versus other nationality. For example, the words evil and wrong is more associated with Middle Eastern country versus right and good is more associated with North American countries, right? So this is another example of course, now this is a simple example of using linear projection to try to remove this bias. All right. And there's more examples here. We have a lot of, okay, there's also a religion example here, right? So this is, again, more triggering, but I want to show it because this kind of bias exists, right? So again, if you actually look at different religion, how those religions associate with different adjectives, this does exist in the word embeddings that we're using to train machine learning models, okay? So now, anyone interested in creating a new example as we play with this? Yes,
Sorry, I have one more question.
yes, go ahead.
How do you know out of like all the 50 dimensions which one to project onto?
Oh.
Like, it seems like
Oh, no, the projection is through, it's a good question. So there's various ways to do dimensionality reduction. That is by itself a topic. So if you have a 50-dimensional space, there's two types of dimensionality reduction techniques in general. One is linear dimensionality reduction. Like PCA is considered one linear dimensionality reduction. There's nonlinear dimensionality reduction, for example, t-SNE, MDS, eigenmap. In fact, scikit-learn has an entire package that is dimensionality reduction. So you can choose any one of them. We choose linear dimensionality reduction because it's slightly more interpretable when you look at the projections, right? Because it doesn't have a non-uniform distortion. It has distortion, but the distortion is sort of better understood than nonlinear dimensionality reduction. Answer your question? Okay, good. So anyone interested in providing for me an example, a simple example of the type of bias you want to explore, and we can play with it? Any idea? Or we can modify existing ones. All right, the tool itself is enable you to kind of explore what sort of bias you want to study. Yes, go ahead. What's that? Wealth and poverty. Okay, so let me see. Let's do linear projection. Okay, so do you want to do gender? Do you want to do what is
How about
country? Okay, perfect. Let me just modify one of this nationality one. Okay, so this is nationality. Let me put it. What other nationalities you want to look at? Like a pair of nationalities. Well, see, pool. What is a? So let's do James. Okay, now it's a spelling test. Did I get it right? What other countries? How about India? China? Anything else? Actually, no. Perfect, thank you. All right, what other adjectives do you want to do? Full? Nah, I don't know what that means actually. Hungry versus full, anything else? Rich? Okay. All right, all the okay, I don't know what that means, but okay, so let's run it. Oh, America. Maybe I should lowercase. Jamaica. Oh, should I do all lowercase? All right. The word successful, wealthy, slightly towards Canada, America. The word poor is and dangerous slightly towards the other direction. Right. So yeah, so there are different type of biases that exist in the word embedding. So feel free to explore, and I'm at the end of my hour. So feel free to and let me know what should be improved and so on. And this is an example of trying to use visualization to understand how debiasing works. So before this tool, a lot of the debiasing algorithm is a sort of a black box, but this way you can actually see how the debiasing is changing the geometry of the underlying word embeddings. Okay. I'm at the end of my lecture. If you're interested in this, feel free to talk to me. There's a lot of interesting problems using visualization to study NLP type problems, and in this particular case, ethics.